Hello again. So, chapter 2 now, from the beginning of infinity. It's called Closer to Reality. It's a much shorter chapter, and so that's helpful for me because I don't have as much time today. So I will read through parts of it once more, and I might make a few comments along the way. It's called Closer to Reality because David is writing about how it is that we come to understand reality better. In other words, come closer to it, closer to our understanding of it, through our science and technology. These things, even though they might appear at first glance to put things between us and that reality, they're the very things that help bring us closer to the reality. And so he makes a very powerful point about that. He begins by through providing a personal anecdote. And this is where, as a graduate student, he's talking about how he was working with some fellow students, and I'll just read the parts that are relevant to set the scene. He was observing galaxies through microscopes, and he continues. That is how astronomers used to use the Palomar Sky Survey, a collection of 1,874 photographic negatives on the sky on glass plates, which showed the stars and galaxies as shapes on a white background. And so David looked at one of these, and he describes how he encountered difficulties. So I continue. Well, he continues. One reason is that it is not always obvious which are galaxies and which are merely stars or other foreground objects. Some galaxies are easy to recognize. For instance, stars are never spiral or noticeably elliptical, but some shapes are so faint that it is hard to tell whether they are sharp. Some galaxies appear small, faint and circular, and some are partly obscured by other objects. Nowadays, such measurements are made by computers using sophisticated pattern-matching algorithms. But in those days, one just had to examine each object carefully and use clues such as how fuzzy the edges looked. Though there are also fuzzy objects such as supernova remnants in our galaxy, one used rules of thumb. How would one test such a rule of thumb? One way is to select a region of the sky at random and then take a photograph of it at higher resolution, so that the identification of galaxies is easier. Then one compares those identifications with the ones made using the rule of thumb. If they differ, the rule is inaccurate. If they do not differ, then one cannot be sure. One can never be sure, of course. So I'll just pause there. He says, one can never be sure, of course. Now, David says this often. All fallibilists do. I often bring it up as well. But this idea of being sure or being certain, it's a remarkably pervasive thing. It's this anti-fallibilism. Now, scientists and philosophers, as well as religious dogmatists, as well as people who believe in certain kinds of religious certainty, are subject to this. So I've written a few notes about my thoughts on it. So lots of people seem to want complete or final answers. So people seem to seek final answers in a way. Even at the very beginning of infinity, David begins chapter 1 with a quote from John Wheeler, made back in 1986, and I'll just read it for you. And he writes, or John Wheeler has said, "Behind it all is surely an idea so simple, so beautiful, that when we grasp it in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise?" So the Wheeler quote, I think, can be interpreted in one of two ways. Either he's seeking a foundation, or perhaps even some kind of certainty, or on the other hand, he's seeking a fundamental theory, and I think he's seeking a fundamental theory. But there's a misunderstanding, I think, at times, between what people who are interested in fundamental ideas are doing and what people who are interested in final theories are seeking. There's a huge difference. A fundamental theory is a theory that is implicated in many other theories, which lies beneath many other theories. And so it's fundamental because it's below other things. But it's not necessarily foundational. So I think there is this difference between fundamental and foundational, or even infallibilist. But some people might get the sense in that quote that there's something anti-fallibilist going on, that behind it all. And so we get to a final theory that is so simple. Now, I think that would be a misinterpretation, but I can understand how someone might read it that way. Whatever the case, there is a pervasive meme out there that what we are seeking in science are final answers. It still exists. It's in the vernacular. I think it might come from religion, and this is pure speculation, and I think that might come from evolution. What I mean is that parents have almost always, until very recently perhaps, taught children in this way of, don't do it, I'm certain, are you sure, I said no, you must do this, you have to do this, there is no option. So parents tend to speak in these infallibilist ways, these authoritarian infallibilist ways. It's kind of ingrained in the culture. I think that's what might have come first. Now, it's a useful first guess for our ancestors who probably got it from evolution. This idea that you simply need to do what you're told because what I've done worked, and so what I did is going to work for you. It's the only thing I do know, so therefore you better do it, or you'll die, something like that. And so if this worked for adults to children, better than simply allowing children to do absolutely anything they want, in other words, rediscovering the entire world themselves without any help, which is really the function of parents, to help children to understand the world, to navigate in ways through the world that children themselves would appreciate and find fun doing. But before you can have that kind of more nuanced view about children, the precursor is do as you're told. So children are taught sometimes, I think, by this anti-fallibilism idea. It's ingrained. I think it came first. I think it probably came from evolution. Adults then spoke in infallibilist ways to each other because that's the way they were taught as children. That evolved probably into some kind of moral laws and about a need for certainty, and possibly out of this a metaphysics arose that again was founded on some kind of certainty that the gods absolutely existed and that you had to believe in them because they're definitely there. And so culture is saturated with this, and history has been as well. Political movements have been. And the key is these things are not extinct because although some of us realise at root there's this poisonous common core to all of this, it doesn't mean that everyone is going to be a fallibilist. The default position appears to be in culture now to be anti-fallibilist, to believe in certainties, to believe we can get to some final answer that will be unchanging. And it doesn't matter if you are a respected scientist or a philosopher or a rationalist, it's quite possible to nevertheless be saturated in anti-fallibilism, and yet and people are revealed by the ways in which they speak as to whether or not they fundamentally endorse this idea that you can reach final answers in science. You can have complete answers. Let's continue with the beginning of infinity, and where David is talking about looking at galaxies through a microscope because they're on photographic plates, which is the way it used to be done. He says, I was wrong to be impressed by the mere scale of what I was looking at. Some people become depressed at the scale of the universe because it makes them feel insignificant. Other people are relieved to feel insignificant, which is even worse. But in any case, those are mistakes. Feeling insignificant because the universe is large has exactly the same logic as feeling inadequate for not being a cow or a herd of cows. The universe is not there to overwhelm us. It is our home and our resource. The bigger the better. Again, here's one of those ways in which David provides a subtle introduction or preview for things to come. And this is a powerful point, and it's one of the ones that is most swiftly rejected in my experience when they encounter these ideas. This idea that the universe is our home. And if we take that seriously, that it's not merely our own residence, or even our planet, even our solar system, but the universe is our home. It contains our resources. It is a hostile environment, but home nonetheless. It's not out to kill us, but it's also not out to sustain us. We, and the knowledge that we produce, is the thing that enables us to control the implacably vast and hostile universe. And so we need to work with the universe. It's not against us, but it's not going to go out of its way to help us either. It's not a thinking thing. And he says the bigger the better, and as far as we know, it seems as though the physical universe is infinite. He continues, but then there is the philosophical magnitude of a cluster of galaxies. As I moved the crosshairs to one nondescript galaxy after another, checking at what I guessed to be the centre of each, some whimsical thoughts occurred to me. I wondered whether I would be the first and last human being ever to pay conscious attention to a particular galaxy. I was looking at the blurry object for only a few seconds, yet it might be laden with meaning for all I knew. Okay, so this is where I'll try and summarise the remainder of what he says there, but I would urge everyone to read it because his summary is far more eloquent than... his actual words are going to be far more eloquent than my summary. But essentially he says that this process is error-prone in a sort of humorous way, because as a non-expert looking at these galaxies, he's prone to the kind of errors that he's prone more frequently to the kind of errors that someone who is expert in this might not be. And so as he's thinking about whether or not a particular galaxy that he's looking at is one that no person on Earth will ever look at again, nor has ever looked at, he thinks perhaps there are planets orbiting stars in that galaxy that he's looking at, and on those planets are civilizations, and those civilizations have long histories and culture. And he's thinking all this, and his mind is kind of expanding to the realization that there could be so much meaning embedded in that picture, in that image, that at least embedded philosophically in that image, that what is behind those pixels on that photographic plate, what is behind those little smudges on the photographic plate is a huge amount of meaning. What he does actually say is he asked the person that he was working with, he says, "Is that a galaxy or a star?" "Neither," was the reply. "That is just a defect in the photographic emulsion." The drastic mental gear change made me laugh. My grandiose speculations about the deep meaning of what I was seeing had turned out to be, in regard to this particular object, nothing at all. Suddenly, there were no people in that image. There was no culture. There was no history. And it all just vanished really quickly. So he made a mistake. Then he goes on to say, "But wait, was I ever looking at a galaxy? All the other blobs were in fact microscopic smudges of silver too. If I misclassified the cause of all of them because it looked too much like the others, why was that such a big error?" He says, "Because an error in experimental science is a mistake about the cause of something. Like an accurate observation, it is a matter of theory. Very little in nature is detectable by unaided human senses. Most of what happens is too fast or too slow, too big or too small, too remote or too hidden behind opaque barriers, or operates on principles too different from anything that influenced our evolution. But in some cases, we can arrange for such phenomena to become perceptible via scientific instruments. We experience such instruments as bringing us closer to reality, just as I felt while looking at that galactic cluster. But in purely physical terms, they only ever separate us further from it. I could have looked up at the night sky in the direction of that cluster, and there would have been nothing between it and my eye but a few grams of air. But I would have seen nothing at all. I could have interposed a telescope, and I might have seen it. In the event, I was interposing a telescope, a camera, a photographic development laboratory, another camera to make copies of the plates, a truck to bring the plates to my university, and a microscope. I could see the cluster far better with all that equipment in the way. So this is profound. This idea that the technology that human beings have created because of our scientific knowledge then is the very thing which allows us to get closer to reality, but in a sense it puts physical barriers between us and that reality. But the reason that we do that is in order to help us correct our errors, to constrain what we know. I had a similar experience when, although I studied astronomy at university, I didn't tend to look through telescopes very often at all. What I did do was use computers. So we had the Swinburne University supercomputer, which is basically just a whole bunch of normal computers, but all working in parallel together, a room full of normal computers working in parallel, and they call it a supercomputer. And what we used to do were galaxy simulations. We used to collide galaxies together, and in particular I looked at one called ARP 271, and this was a pair of spiral galaxies that is in the process of colliding. Of course, all that is seen by astronomers when they look through telescopes at a galaxy like that is a static picture. The motion of the stars, let alone the two galaxies, is occurring on scales of millions and hundreds of millions of years. It is reasonable to presume that no one alive today is going to see much in the way of motion of those two galaxies in reality. We do not see them moving, but we know they are. At least we do not see them moving with our naked eye. We know they are because we can detect, when we look more closely, the redshift of the stars. The spectra of stars reveals the direction in which parts of those galaxies are moving, and so we can see that they're actually moving together. We can also determine by the same methods how massive the galaxies are, because with spiral galaxies they are literally spinning, and the faster they're spinning the more massive the galaxies are, and so you can have an estimate for the mass of the galaxies. So you can find an estimate for the velocity and you can find an estimate for the mass. Then what you can do is you can put some of this data into a supercomputer, and then what you can do is you can try to guess what's going to happen next to the two galaxies during the collision and after the collision. Will they merge together? Will they pass through one another? It's actually possible for spiral galaxies that collide to pass through one another. Not unaffected, but they will pass through and keep going. They're kind of like clouds. It's very unusual, highly unlikely for stars themselves to collide, even though the galaxies have, because there's so much empty space in between the stars. And so we will never see this galaxy pair actually colliding. We will never see, by which I mean able to observe the consequences of the predictions that we make, unless we're still around in a long time, some hundreds of millions of years. What I predicted would happen is that they would indeed combine into one single galaxy. But that's based on the output of a supercomputer, and it's based on a very low resolution prediction, by which I mean not only do we make assumptions which are very error prone about the masses of these two galaxies and the velocities of these two galaxies, we cannot possibly, with our current technology, with our supercomputer technology, simulate the collision of two bodies, each of which contains some hundreds of billions of stars. If you want to find out what happens when a couple of hundred objects over here combine with a couple of hundred objects over there, this is the famous n-body problem. And that quickly becomes intractable. It's very difficult to try and figure out what all those particles are doing in response to each other. So what you do is, instead of assuming that you've got some hundreds of billions here and some hundreds of billions here, you can just use some millions here and some millions here. And so you've only got some very, very tiny fraction of the actual number of objects here and here. And then assuming that when they collide, it is similar to what happens when you've actually got the hundreds of billions. Whether or not that's true will be sorted out in years to come as the computers get more powerful, and we can see whether or not we're converging on the same answer. But all this is to say that all of this technology, supercomputers and the software that runs on them, and the observations that we make using telescopes, enable us to see into the distant future. It's a blurry image, but it's better than a random guess. And the better our technology becomes, the more resolution we have about the future, about predicting the future. And this is a genuine kind of prediction. I'm fond of talking about prophecies, where people have really unconstrained ideas about the function of knowledge. But unless we have a particular interest, or some people have a particular interest somewhere in doing something with ARP 271, I think it's fair to say that given the sheer number of galaxies and stars in the universe, it'll be some hundreds of millions of years before anyone's interested in going to ARP 271 and trying to, use the resources there. Okay, so that was a long diversion. Let me go back to the beginning of infinity. Okay, and I'm jumping around a little bit here, but this is another interesting part a few pages back, where he says that computers nowadays do the cataloguing of galaxies rather than having graduate students look at photographic plates. And he says, the computers that nowadays catalogue galaxies may or may not do it better than the graduate students used to, but they certainly do not experience such reflections as David had as a result. I mention this because I often hear scientific research described in a rather bleak way, suggesting that it is mostly mindless toil. The inventor Thomas Edison once said, "None of my inventions came by accident. I see a worthwhile need to be met, and I make trial after trial until it comes." What it boils down to is 1% inspiration and 99% perspiration. Some people say the same about theoretical research, where the perspiration phase is supposedly uncreative intellectual work, such as doing algebra or translating algorithms into computer programs. But the fact that a computer or robot can perform a task mindlessly does not imply that it is a mindless task when scientists do it. After all, computers play chess mindlessly by exhaustively searching the consequences of all possible moves. But humans achieve a similar looking functionality in a completely different way, by creative and enjoyable thought. Perhaps those galaxy cataloguing computer programs were written by those same graduate students, distilling what they had learned into reproducible algorithms, which means that they must have learned something while performing a task that a computer performs without learning anything. But more profoundly, I expect that Edison was misinterpreting his own experience. A trial that fails is still fun. A repetitive experiment is not repetitive if one is thinking about the ideas that it is testing and the reality that it is investigating. That galaxy project was intended to discover whether dark matter, see the next chapter, really exists, and it succeeded. If Edison or those graduate students or any scientific researcher engaged upon the perspiration phase of discovery had really been doing it mindlessly, they would be missing most of the fun, which is also what largely powers that 1% inspiration. So this is important, and this is a theme that we will come back to, that what people are is different to any other entity in the universe that we know of. We are creative. And so even if we're going through an uncreative perspiration phase, apparently, we're doing something very different than if an automated machine was taking that task for us. We are able to think about each of the steps. We're able to think about other things while we're doing it. And so we are necessarily creative at all points. So now, what's the purpose of scientific instruments? I prefaced this at the beginning of the video, So let me return to the text now. The primary function of the telescope's optics is to reduce the illusion that the stars are few, faint, twinkling, and moving. The same is true of every feature of the telescope, and of all other scientific instruments. Each layer of indirectness, through its associated theory, corrects errors, illusions, misleading perspectives, and gaps. Perhaps it is the mistaken empiricist idea of pure, theory-free observation that makes it seem odd that truly accurate observation is always so hugely indirect. But the fact is that progress requires the application of ever more knowledge in advance of our observations. And so he says, even though he was mistaken in one case when he was looking at one of the smudges on the photographic plates, misinterpreting that smudge as a galaxy when it just turned out to be a fingerprint, that concern that the rest of the images that he was looking at were similarly just smudges or weren't galaxies for some other reason can't be true. Because the point is that our knowledge and our technology corrects errors like that. He didn't have the knowledge at that particular point, but the other expert did. And so he says, so I was indeed looking at galaxies. Observing a galaxy via specks of silver is no different in that regard from observing a garden via images on the retina. Okay, so I'm going to the conclusion now. This is a fast chapter. It's a good chapter. And so he continues. Explanatory theories tell us how to build and operate instruments in exactly the right way to work this miracle. Like conjuring tricks in reverse, such instruments fool our senses into seeing what is really there. Our minds, through the methodological criterion that I mentioned in Chapter 1, conclude that a particular thing is real if and only if it figures in our best explanation of something. Physically, all that has happened is that human beings on Earth have dug up raw materials such as iron, ore, and sand and have rearranged them, still on Earth, into complex objects such as radio telescopes, computers, and display screens, and now, instead of looking at the sky, they look at those objects. They're focusing their eyes on human artifacts that are close enough to touch, but their minds are focused on alien entities and processes light years away. Sometimes they are looking at glowing dots, just as their ancestors did, but on computer monitors instead of the sky. Sometimes they are looking at numbers or graphs, but in all cases they are inspecting local phenomena, pixels on a screen, ink on paper, and so on. These things are physically very unlike stars. They are much smaller. They are not dominated by nuclear forces and gravity. They are not capable of transmutating elements or creating life. They have not been there for billions of years. But when astronomers look at them, they see stars. So this is profound. And this is the idea that we do not experience reality directly. And even if we were to take away all of that instrumentation and technology, and we were to lay on our backs and look up to the night sky and see a star, what's actually going on, as David mentions in his TED Talk, and I think he talks about this in Chapter 1, I didn't mention it, is light, photons, are striking the back of the retina, eventually, once they get through the cornea, and causing electrical signals to be sent via the optic nerve back to the brain, and in the brain some neurons are crackling away. They're communicating with one another, and that's what we are. Okay, so we are a mind that's inside of that brain, and however the mind works, it depends, at least in part for now, on how the neurons transmit electricity to one another. That's what we are. Everything else is interpretation. Our brain has to interpret the signals coming from the optic nerve. The optic nerve is only sending signals because light has been detected at the retina, and that light has only been detected at the retina because it somehow or other made its way through the atmosphere from the star. So this process of seeing stars or seeing anything is an extremely complex phenomena where there are many layers of interpretation between your mind and the reality out there. So that's Chapter 2. I'm not sure when I'll get to Chapter 3. We'll see. It could be some weeks. But this has kind of been fun. See you.